Hello everyone, welcome to my class. Today we will move further in investigating interference. Yeah. Now we are in module 4 and we have already studied interference of light waves. We also talked about the role of polarization in the formation of interference fringes, and we also touched upon Young's double slit experiment in our last class. We studied the experimental arrangement, experimental setup, and we talked about the fringe positions, and then we talked about fringe width. Now, once these things are known, in today's class we will solve a few examples. The first example is given here. In this problem, we are given two plane waves which are superimposing in a space, and these plane waves are inclined with some angle, and this angle is shown here in this figure. This k1 represents the wave vector of first wave and k2 represents the wave vector of the second wave, and k1 is inclined at angle theta 1 with respect to the horizontal axis, which is z axis in our case, and k2 is inclined at angle theta 2 with respect to the horizontal axis. Now, let us figure out the expression for wave vector k1 and wave vector k2. Okay. Now, as you see in the figure, the k1 is making an angle theta 1 with z axis, and therefore 90 minus theta 1 with y axis. Yeah, this angle is 90 minus theta 1. Okay. And this dashed line, they represent the wave front or phase front, which is plane in our case. Therefore, they are represented by dashed straight line. Now, let us go into the expression of k1. Now, k1 is expressed as k sin theta 1 into minus of y cat. Y cat is unit vector along y axis. Now, you see that k is directing in this direction. Okay. Since k is pointing in this direction, and in this direction z axis is positive while y axis is negative, it is going down. Therefore, there is a negative sign here before y cat. Okay. And theta 1 is the angle which the ray makes with the horizontal z axis as stated before. And since we are now finding the component of the wave vector along y axis, therefore, this angle would be of importance, and this is our 90 minus theta 1. Therefore, cosine of 90 minus theta 1 would be sin theta 1. Yeah. Therefore, we have sin theta 1 here, k is the magnitude of the wave vector and y is the unit vector, and minus sign represents that y is in opposite direction. Similarly, in the z component of the wave vector k1 is expressed by this second term, where z cap is the unit vector along z axis, and k cos theta 1 is the component of this vector along z axis. Okay. It is k1 here, and this angle is theta 1. Therefore, the component would be k1 cos theta 1. Okay. K1, and here we can take if we take the mod of k1, that is equal to k, and z cap represents the unit vector along z. Similarly, we can express the wave vector k2 in its component form, which is shown here. Yeah. Now, instead of theta 1, it is theta 2 here, because the second wave is inclined at angle theta 2 with respect to the horizontal, and now you can see that k2 is going in this direction. Okay. Since k2 is in this direction, this is your theta 2, this is your 90 minus theta 2, and for k2 in its component form, both the components are aligned along along y and along z, which are in positive y and z direction, and therefore, we do not have minus sign before y cap or before z cap. Okay. Now, once we have the expression for k1, wave vector k1 and wave vector k2, we can write the corresponding expression for electric fields. Okay. Now, for the first wave, electric field can be written as E1 is equal to E E01 or E01 is the amplitude of the field, and then the phase part cos k1 dot r minus omega t. Let us write k1 in its component form, and then this is our k1. Okay, this is the first expression. Now, similarly, we can write the expression for E2, and E2 is E naught 2 cos k2 dot r minus omega t here. And now you see that once you take the dot product of k1 with vector r, then the unit vectors are gone here, which is obvious, okay, because r is a vector which also have its component here. It has x component, y component, z component, and if you write this vector in its component form, then you can write r as x cap into x plus y cap into y plus z cap into z. Yeah, if you write it in this form and then take the dot product of k1 with r, then you will get this expression. Similarly, for k2 dot r you get this expression here. Now, therefore, we have the expression for electric field of both the waves as E1 and E2, which are given by equation 35 and 36 respectively. Okay. Once the expressions for electric fields are known, then to have the resultant expression, what we will have to do is that we will just sum them up. Okay. But before that, let us assume or let us simplify our problem, and for this simplification we assume that the field amplitude, the field magnitudes of the two waves are the same, and which is equal to E naught, and the angle of inclination theta 1 and theta 2 is also same, and we assume the two to be equal to theta. Okay. And we are also assume that the electric field are along the same direction, they are the state of polarization is same in both the waves. Okay. Under these assumptions, our problem become very simple, and we can easily calculate the resultant field. How to calculate the resultant field? Add the two vectors or add the two field, and what are the two fields? E1 and E2. Yeah. Therefore, the resultant E would be equal to E1 plus E2, and if we perform some simple mathematics, then this is the final expression which we would be left with. Okay. And the resultant disturbance or resultant field would be given by the resultant field is given by equation number 37 here. Okay. Once the resultant disturbance is known, we can quickly calculate irradiance. Yeah, how to calculate the irradiance? Take the time average of E square. Yeah. And this is what is done here, and the irradiance or the intensity on the screen is given by equation number 38. Yeah, this is the final intensity. Once the intensity is known, then we can calculate. Yeah, once the intensity distribution is given, then we know the fluctuations in intensity. We know the places where intensity is maximum, and we know the places where intensity is minimum, and thus forming the fringe pattern. Once fringe pattern is known, we can calculate the fringe width here. Now, how to calculate the fringe width? Okay, we know that this is a, if you plot it, you will get straight line fringes on the screen. Okay. For maxima, this condition holds good, because you know that this expression is nothing but I is equal to 4 I naught cos square del by 2, yeah, where del is your phase difference. Now, ky sin theta is del by 2, therefore, del would be equal to 2 ky sin theta, and for maxima this phase must be equal to integral multiple of 2 pi. Yeah. Here n is nothing but an integer. Okay. Now, from here this is since we know the condition of maxima. Now, we will pick two values of y on the screen, y1 and y2, which represents the position of two consecutive maxima. Okay. Once the position of two consecutive maxima are known, we can subtract that and find out the fringe width. Yeah. This is what is done here. Yeah. This we know. From here we can calculate y1 minus y2, which is nothing but your fringe width. Yeah. This is your fringe width. Okay, this we have already done in Young's double slit experiment, therefore, I am not going in too much detail. Now, once y 1 minus y 2 is known, fringe width is known, and therefore, what we saw is that given the direction of wave propagation, we can calculate the expression for field. By summing them up, we can calculate the total field distribution. From there, we can calculate irradiance distribution, and from there we can calculate fringe width, and fringe width is proportional to lambda. Yeah, larger lambda is, larger would be the width of the fringe. This is all about problem number 1. Now, we will move to second problem. Yeah, the second problem is that we have a screen P P prime, which is represented here this by this vertical line. Now, a plane wave is propagating normally towards the screen P P prime, okay, and there is a point source O which is kept here, and from this point source spherical waves are getting generated and they are also propagating towards the screen. Okay. The question is, when the plane wave interfere with this spherical wave, then what type of fringe pattern will be generated on the screen. Okay. Now, as a solution, now consider the interference pattern produced on P P prime by the superposition of plane wave incident normally and a spherical wave emanating from point source O. Yeah, this is what is given. Now, to find out the expression for the resultant distribution, or to find out the intensity distribution of the resultant disturbance, what we will have to do, we will first have to write the expression of electric field for plane wave, and then write the expression for electric field for a spherical wave, and then sum them up, and from this resultant field we will have to calculate the irradiance, and then we will plot the irradiance to see the fringe pattern or the type of the fringes which the observer will observe on the screen P P prime. Okay. We all know that the plane wave is given by this expression here, E naught cos k z minus omega t plus phi. Phi is initial phase, and k is the wave vector or wave number, and z is the direction of the propagation here. This is given here. Yeah, z is the axis which is pointing towards the screen P P prime and is normal to the plane of the screen. Okay. Therefore, equation number 40 represents an expression for electric field of a plane wave. Okay. Once the expression of plane wave is known, then our next target is to find out the expression for a spherical wave. Okay. We have already studied about the spherical wave, and the expression for electric field for a spherical wave is given by equation number 41, and here you see that in the denominator we have r. Yeah, A naught is the magnitude or amplitude of the wave, r is sitting in the denominator, and in the phase part we have k r minus omega t. Yeah, it is not k z, but it is k r now. Yeah, it is a, because spherical wave propagate in all possible directions. Yeah. Now, r is measured from origin or source O. Yeah. Now, once we have the expression for field, we will do some mathematics to simplify things, to write to express r in terms of x and y. Yeah, because the plane wave is written in terms of z. We will also try to reduce the expression for the electric field of a spherical wave in Cartesian coordinate system. Yeah. Now, r can be expressed by this relation. Yeah, x square plus y square plus d square square root. Yeah. What is d then? D is the distance between point source O and the screen, as shown here in this figure number 7. Yeah. Once d is known, it means the value of z where our screen is kept is d. Okay. And we know that r is equal to square root of x square plus y square plus z square, and at place of z we will write d here. Yeah. And this d is very huge as compared to x and y. Yeah. If you remember, then we always try to observe interference fringes close to the center of the fringe, sorry, center of the observation plane. Now, in this expression of r we will take d out, and this is the final expression of r which we are left with. Now, applying this condition which says that d is much larger than x and y, in this particular case we can do this binomial expression here and neglect higher order term, because d is a very large quantity and therefore, the next order additive term would be very small and we can safely neglect them. And the final expression for r in this particular case is given by equation number 43. Now, let us substitute the expression of r into the expression of field of spherical wave. Yeah. Here it is the resultant field. The expression of E1 is given by this relation, where we have replaced z by d. Again here r is replaced by d here, because we are interested in screen, and particularly in the region of the screen which is close to the center point of the screen, means this region we are interested in. Okay, therefore, r here is replaced by d in this expression. In the phase part, r is replaced by this equation number 43. Okay. And therefore, if you square this equation and take the time average, then we will get equation number 44, because the time average of a square of cos theta is half. Therefore, here we are getting E naught square by 2. Similarly, this term time cos square theta would be half, time average of cos square theta is half. Therefore, we get A naught square d square by 2, this is correct. Now, we will have a cross term also here, because it is a plus b, and if you are squaring it, then you will get a square plus b square plus 2ab. 2ab information is here, this is the cross term. Okay. And then if you take the time average of this term, then the resultant expression looks like this. Yeah, this is the final irradiance at the screen P p prime. Now, let us further simplify this equation number 44 by assuming that A naught by d, which is nothing but magnitude of a spherical wave at the screen, is equal to E naught. Okay. We are assuming that the magnitude of electric field and magnitude of electric field of a spherical wave and the magnitude of electric field of the plane wave are the same at the observation screen, which is P p prime in our case, yeah, which are shown here in this figure here. P p prime is this screen. Okay, under this assumption, what we can do is that we can replace A naught by d with E naught. Okay. With this, equation number 44 reduces to equation number 45. Okay, because this is again equal to E naught square, and therefore, the first two term would be equivalent to E naught square. Yeah, because this first one is E naught square by 2, second is also E naught square by 2. Therefore, these two term collectively would be equal to E naught square. Here too, these two term would be equal to E naught square, and what is left is cos k by 2 d x square plus y square minus phi. Just by looking at this expression, you can see that this is symmetric in x square plus y square, it is forming a circle here in the phase part. Yeah. Therefore, we will obtain a circular interference fringes. Just by looking at equation number 45, we can guess this. Yeah. If you vary an x and y, then you will rotate it on a circle. Yeah. Therefore, if you interfere a plane wave front with a spherical wave front, then on the screen we will have concentric circular fringe pattern, which would look like this. This is concentric circular fringe pattern. Okay. Now, this is all about problem number 2. Now, we will move to our next problem, and the description of next problem is as follows. We have two slits which are S1 and S2, and a plane wave is met to incident on this slit at an angle theta with respect to the horizontal line. Yeah, this is the horizontal axis, and with this axis the plane waves make an angle theta. Okay. And now we are observing the fringe pattern at the screen, which is at a distance capital D from the source plane. Yeah. The plane in which sources S1 and S2 are is called source plane, and the plane in which we are observing the fringes is called observation plane. Okay. The source plane is at a distance d from the observation plane or plane of observation. Okay. Now, consider a parallel beam of light incident at an angle theta on two slit S1 and S2. Okay. Now, since the light is not being launched perpendicular to the source plane, therefore, there would be a path difference between the lights which are falling at point source S1 and the light which is falling at point source S2. How to calculate this path difference? We will draw a perpendicular from S1 to the ray which is falling to S2. Okay. And x S2, the length x S2 is the extra path which the light ray travels when it falls on sources S1 and S2. Yeah. The light which is falling at source S2 is travelling an extra path of x S2 as compared to the light which is falling at source S1. Okay. Therefore, the path difference between the waves emanating from slit S1 and S2 is given by x S2, and which is equal to d sin theta. What is d? D is separation between the two sources S1 and S2, and theta is the angle which the incident light makes with the horizontal. Okay. Now, how to calculate the intensity distribution? The intensity distribution on the screen due to S prime is some source which is very far from S1 S2, and when the light travels this distance it becomes almost plane wave, and this plane wave is falling at some angle with respect to the horizontal. Yeah. Now, we know that the intensity distribution is given by equation number 47, I is equal to 4 I naught cos square del by 2. Our task is to calculate or to find the expression of phase del. Okay. Now, how to calculate del? To calculate del or to calculate the phase difference, we have to find the path difference through this schematic diagram. Once the path difference is known, just multiply it with k. Yeah. What is k? K is nothing but 2 pi by lambda. Okay. It means that this is our path difference. In traditional Young's double slit experiment, path difference is equal to S2p minus S1p. Yeah. We draw a line from S2 to P and from S1 to P, and we take the difference between these two paths, and this difference gives us the path difference between the two ray paths. But in the present case, when the ray emanates from the two sources, it is having a priori path difference, which is x S2, which is d sin theta. Therefore, the S2p path will have an additional path difference, which is x2 s. Therefore, to calculate the final path difference, we have to sum these two quantities. Okay. What are these two quantities? The first is x S2, which is the extra path which light ray travel when it reaches to S2, and then S2p. Okay. And therefore, equation number 48 gives us the phase difference. Okay. Now, let us substitute this, the phase difference del is equal to 2 pi by lambda S2p minus S1p, and d is your x S2. Yeah. This is the expression for x S2, which is d sin theta. but we know from Young's double slit experiment S2p minus S1p is equal to y small d by capital T. Small d is the separation between the two sources and capital D is the separation between the source plane and observation plane. Okay, this we have already derived in Young's double slit experiment. Okay. Once these phase difference is known, we can easily calculate the intensity distribution. Okay. Then we will substitute equation number 50 back to equation number 47. Okay. And this expression gives us the irradiance or intensity distribution at the screen. And this term you see, there is this additional phase term due to the inclination of the phase front, due to the inclination of the plane wave which falls on the source screen. Okay. This is all for today, and thank you. See you all in next class.